So today we're going to be summarizing our periodic table trends and what we've been talking about so far. So we'll go over atomic size, ionization energy, and we'll finish off with electronegativity. So let's start with atomic size. Well, by definition, we're talking about how large that the atom is. And we have to remember that that size is measured by what we call atomic radius. So if I think about what atomic radius is, let's say that that circle is representing my atom. It would be the radius of that circle, which starts at the nucleus and ends at the valence electrons. So you have to be able to recognize those points by terminology, where the center is where our nucleus is, and the outermost part of that circle is where we have our valence electrons. So that's my atomic size. Now, if I think about how that trend happens on the periodic table, these are just arrows that you have to memorize. So I know that my atomic size gets bigger as I go down, and it increases going to the left. So if I were to draw one arrow that summarizes the change in atomic size, everything is increasing in this direction. And for this video today, I'm going to draw the arrows in the directions that things are increasing. So I won't draw any arrows in the way that things are getting smaller. I'm going to draw all the arrows in the way that things are getting bigger. So that's atomic size. What about ionization energy? Well, by definition, ionization energy is how much energy it takes to remove a valence electron from an atom. So again, if I draw an atom, here's my nucleus, and then I know that I have different rings with different electrons on it. And my valence electrons are the ones on this outside ring. So I'll just draw one. My ionization energy is literally how much energy would it take to remove that one electron from that atom and put it somewhere else. So let's draw the direction in which ionization energy increases. We know that it increases going up and to the right. And so if I had to draw one arrow showing the direction in which things are increasing, that is the arrow I would draw. And I'm actually going to draw them with green so that we can have different colors for our different periodic table trends. So let's change this to green. Okay, and lastly, we can talk about electronegativity. By definition, this is the ability of an atom to attract electrons of a different atom toward itself. So let's say that I have this atom right here. And I know that my nucleus has a positive charge. I know that my nucleus is positive because it has a ton of protons. And so when I think about my electrons that are surrounding this atom, I know that they are being attracted by my positively charged nucleus. We know plus and minus charges like each other, so there's already that level of attraction. But electronegativity is saying, hey, that attraction doesn't have to just stop at our own atom, but I can actually start to attract electrons of a different atom toward myself. So I can take my positively charged nucleus and say, hey, I'm going to attract this electron toward myself as well. And the bigger the electronegativity is, the bigger that ability is. So let's draw the direction in which electronegativity is increasing. It follows the same trend as ionization energy, and so it is going to increase as we move. Let's choose blue. As we go up and to the right. And again, if we had to draw one arrow, that is the direction in which electronegativity increases. So what is our big picture idea? One thing that's really important to understand is that all of these periodic table trends can be explained with effective nuclear charge and the number of electron shells. So we have to be able to understand atomic size, ionization energy, and electronegativity from the perspective of these two things and how they relate to those trends. So remember that effective nuclear charge is the net positive pull that the nucleus exerts on electrons. The net positive charge. Okay, so how much pull basically that the atom has. And then the number of electron shells is the number of rings. So when I draw my rings around my Bohr model, that is what I'm talking about. Now, in this case, when we think about the way that effective nuclear charge and number of electron shells is changing, each has a certain direction that they change in, and they don't change in the other. So with effective nuclear charge, I'll draw the direction in which it increases. So here's the direction in which effective nuclear charge increases. And let me label that with EFC for effective nuclear charge. But here is the direction in which the number of electron shells increases. So I'll call that electron shells. So if I'm looking at the horizontal arrow, I see that effective nuclear charge is increasing as you move to the right. But I have to ask myself, if I'm walking along the right on the periodic table, are my number of electron shells changing? No. Only effective nuclear charge changes when you move from left to right. And similarly, I can ask when I move up and down on the periodic table, is my effective nuclear charge changing? No, because it only changes horizontally. So when I look vertically, I can see that the only thing that's changing is my number of electron shells. Okay, so if I go back and add these arrows onto my different periodic table trends, these arrows are going to help me understand why I see these different trends in atomic size, ionization energy, and electronegativity. So let's go ahead and add it in and see if we can explain what's going on. So here's my effective nuclear charge. And I can see that they are increasing in opposite directions. That the bigger my effective nuclear charge, the smaller my atomic radius. Which makes sense, because if effective nuclear charge is the amount of positive pull from the nucleus, if I have a bigger pull, I'll have a smaller atom. Basically, if this nucleus can pull on these valence electrons more tightly, then I'll bring it in closer and be a smaller atom. If I want to justify this arrow, I know that my number of electron shells or rings is increasing in this direction. So let's just say rings. And it does make sense that if I have more rings, I'm going to have a bigger atom. Okay, how about ionization energy? Well, again, I'll add my arrows on top. So here's my effective nuclear charge. And I can see that the greater my effective nuclear charge, the greater my ionization energy. Which again makes sense, because if I have more of a positive pull from my nucleus, then that outermost electron is going to be harder to remove, right? If things are being pulled in more tightly, it's harder for me to take them out. And what about the number of electron shells? Well, here I have to understand something really important, which is that the electric force is stronger at closer distances. And so when I think about these arrows, I see that when I have less shells, so when I'm a smaller atom, my ionization energy is bigger. And that makes sense because, again, if I think about my positive nucleus, and let's say I have one shell versus my positive nucleus and I have two shells, which electrons are closer? Well, these electrons are closer, the one on that shell instead of the second shell. And so the amount of pull is greater. And again, it's going to be harder for me to remove that valence electron. So I always want to be thinking about, okay, what situations would make my electron harder to remove? And if my electrons are closer to my nucleus, then they are definitely going to be harder to remove. Okay, and lastly, how can we understand electronegativity with our effective nuclear charge and our number of electron shells? So we start with effective nuclear charge. And the rationale is similar here with ionization energy, but slightly different. So with effective nuclear charge, the bigger my EFC, the bigger my electronegativity, which again makes sense, because if effective nuclear charge is my net positive pull, then my ability to attract electrons of a different atom will also be greater, because in general I have more of a positive pull for my nucleus. Versus our number of electron shells or rings, which is increasing as you go down. So again, I can see that if I have less rings, then I have a greater electronegativity. And this points to the same idea. The electric force is stronger at closer distances. So if I'm thinking about my positive nucleus being able to attract negative electrons from a different atom, if I'm smaller in general, then I can get closer to the neighboring atom and I can exert a bigger force on those electrons from the different atom and pull it toward myself. And if you need a drawing to help us out with that, let me draw a little figure. So again, let's say that I have, this is 2 rings, and let's compare it to an atom that only has 1 ring. And let's say that I am trying to attract electrons from this atom. So how well can I take an electron from this atom? I'll draw the same one twice. Well, if my electronegativity is how well this nucleus can pull on this electron, I can see that I can bring this guy closer than this atom just based on where that outermost ring is or how many rings I have. And so this atom over here is going to be able to exert a greater force on that electron than this one because it can bring it closer to itself. So those are our periodic table trends. And again, the most important thing is that you can take this big picture idea of effective nuclear charge and number of electron shells and connect it back to these different topics.